Okay, thank you. So what I've done is, in order to keep the conversation flowing, I have taken out the slides that we wouldn't have been able to speak publicly about, and then we can talk about some of the individual data later on this afternoon. So what I'm going to do is talk about two separate areas and talk about them more in the context of the things we want to do, not to kind of relive what's already been done. And so I'm really going to focus on a couple of areas. First of all, we're going to talk about our current protocol, which includes upfront biopsy, immunophenotyping, and then a stratified treatment protocol for therapy. And this is kind of the primary objective of the study, although another part that will come out of it, which is going to be the second part of the talk, and in some ways I think is going to, in the long run, be much more interesting and probably informative, is a molecular profiling based on some of those findings. That none of the material I'm going to talk about is restricted with respect to. You've got much of what we're going to end up talking about is I've removed all of the drug-specific information so that there's no conflict with any of the drug companies. So these are the institutions that are going to participate in this upcoming study. It actually took us almost a year. Okay, oh, even advancing, okay. It took us almost a year to work this out. As Darren has already pointed out, sometimes many clinical trials are probably doomed before they begin because people didn't spend enough time thinking about some of the issues that would actually ensure their opportunity to be successful. Sometimes a successful clinical trial gives a negative result, but at least if you get a negative result, you know with confidence both that it was negative and why it was potentially negative so that you actually learn something. It's something that unfortunately I think in oncology, and particularly in pediatric oncology, we don't do enough of. We don't learn enough from why things don't work. We only focus on the trials that do seem to quote work, that have activity is the only way to move forward. So one of the concepts of these, for example, excuse me, is that each institution has agreed to standardize the way in which the biopsies are done, the amount of material, the placement of the biopsies. In every single one of those, we thought that that was going to be as important as just getting people to say, sure, I'll participate, because obviously that's the easy part. It's actually doing it that becomes much tougher. Oh, you said I could, okay. So if you said, what's the background for the development of this clinical trial? This is the outcome of one of the most recent COG protocols. Obviously, I could have put up one of 100 other similar Kaplan-Meier curves, and they wouldn't really have mattered. So I don't think anyone in this group, based on the presentations we've already had, really needs the background for why one might want to do a slightly more novel approach. And similarly, the rationale is basically the same as the background, because with that kind of background, you don't really need much more of a rationale. So my goal is not to really focus on the things that I think everyone in this room already feels with their heart needs to change. I think the real fundamental question is, where should we be going? And obviously, by the breadth of talks today, I don't think anybody believes there is a single answer. And so as we talk about our little areas, the idea of how to put some of these together is going to be important. And that's one of the things in which we've spent a large part of our time. So to some extent, I'm going to show you a treatment strategy. And in fact, we're not going to debate whether we should have chosen this drug or that drug, this dose or that dose, this combination or that combination, because to some extent, just like the last 250 clinical trials in diffuse pontine glioma, all of which have been negative, the likelihood that in the first iteration you are going to hit a home run is, we understand, unlikely. And therefore, the real goal is going to be the second part, which is to understand why we're not hitting home runs or even getting on base. Maybe in Europe, I shouldn't be using baseball analogies, since many of you probably don't play baseball. I was born and raised in Canada, and it actually took me a while to figure out some of the baseball terminology, and now, unfortunately, I use it too often. So the primary objective of this study, and this was to get back to one of the points that Darren had already raised, and I can say that we did not talk about this before, so it's good always to know that you think a lot like your colleagues. We have, in all of our approaches in Boston and largely in North America, standardize all of our criteria so that we use the same doses of radiation given in the same way with the same entry and eligibility criteria for all of our clinical trials with diffuse pontine glioma. And obviously we wanted to do that in this trial as well. So in this multi-institutional trial, the outcome, the planned observation for these is going to be event-free survival. You heard conversations about whether event-free versus overall survival is a better format. When we looked, much like Darren has done, looked at the overall survival for patients that relapsed, you'll notice, for example, he showed data of between 1 and approximately 4 months, I think it was. When we looked at the data in a large series, the splay was somewhat wider, and therefore there was so much heterogeneity. You could say that if some patients are surviving 1 month and some are surviving 4, that's a 4-fold increase, one patient to the other. Now, admits it's in a small time period and therefore may not be relevant. And we therefore decided that both overall survival and event-free survival are fraught with problems, and therefore decided to keep it standard with what has been used for the last decade in North America, so that at least we couldn't compare to all of the previous studies, none of which are perfect in any particular way. These are the secondary objectives, and what I did was I have specifically cut out the details, because what I didn't want was for us to start debating why it's age 3 to 21 instead of 3 to 18 or 2 to 21. Basically, the idea is to evaluate progression-free survival, and then for secondary objectives is going to be to look, obviously, very carefully at safety and feasibility of performing a biopsy, the safety and feasibility of obtaining the actual tissue, of the ability to make a histologic diagnosis, the ability to have the tissue to do immunohistochemistry, DNA analysis in these patients with diffuse intrinsic pontine gliomas. And when I refer to diffuse intrinsic pontine gliomas, one of the requirements for the neurosurgeons in this protocol is that if the patient has an exophytic component to their tumor, they're not eligible for this study. If the patient, if you're wondering whether it's a slightly atypical course, even if they meet the criteria, they are not eligible for this study. So the only kids that can go on this study are kids for whom you absolutely, positively know have diffuse intrinsic pontine glioma, because if there's a chance they've got anything else and you put them into this protocol, the ability to do these analyses will be confounded. Now, I should point out that we went back and looked at all of the institutional experience at the Harvard Institutes for kids with diffuse intrinsic pontine glioma in the MRI era that met absolutely the classic, which for us was less than 3 months of symptoms, the classic symptoms that you saw, cranial nerve dysfunction, some cerebellar symptoms and or long track signs with less than 3 months duration, and a classic diffusely enhanced, diffusely and largely usually non-enhancing tumor of the pons. So they had to meet all of those criteria. And surprisingly, at the time of relapse, a couple of those patients actually came back, one with an ATRT and two of them, I think it was, with a PNET, suggesting that even when it's absolutely classic, there's still probably a 1 or 2% error rate in the radiographic diagnosis, and presumably which means it's possible that one of the kids that gets diagnosed on this study will end up not having what we believe to be the right disease, and obviously they are no longer eligible for the therapy if their biopsy proves for them to have something else. The other thing that's being mandated here is all of the patients have to undergo both craniospinal imaging as well as CSF cytology to be sure that we are not missing anything that in other ways would potentially change the appropriateness of that patient for the study. In addition, obviously, we are going to, as a secondary aim, evaluate the toxicity profiles of the 4 different treatment strata. I'll show those to you in a moment. And then again, the exploratory molecular biology analysis. And I'm going to go through some detail at the end to show you what that is, because to some extent, I think this is what's really important in this whole process. So this is going to be the approximate schema. Again, the timelines are imaginary. So obviously, you don't have to wait 7 days from when you get your diagnosis to get your image-guided biopsy. The concept is that patients who will meet the strict definition of the disease will go on to image-guided biopsy. The techniques used by the different institutions will differ a little bit, and I'll show you why, but still within the context of where we think it's appropriate for accrual on the protocol. If we only allowed institutions that image and do intraoperative procedures the way we do, the number of institutions that could participate would be so low, these kinds of studies could never be done. And as Darren showed you for some of the other data, particularly with respect to the French series, it's pretty clear that things have moved forward. It's safe to do these kinds of biopsies as long as the people are committed to doing them properly, and therefore all of the image guiding that we're going to use in Boston may not be required by all institutions. At that point, you will have your material analyzed for a variety of things. The two most important ones in the current design are for EGFR and MGMT, and I'll explain that momentarily. Obviously, if your operation is on a Friday, some of this analysis is not going to be completed until the following, Thursday-ish, which is why it gives you up to 7 days. Obviously, if you went for biopsy on a Monday, this might well be done by Wednesday or Thursday at the latest. So exactly how long it takes, there had to be some flexibility, recognizing that the importance of getting children with diffuse intrinsic pontine gliomas into therapy pretty quickly is going to be important. And then as soon as this analysis is done, so you don't have to wait actually until day 8 if it's known previously, you stratify them based on their phenotype, and then you get therapy started. So this is a stratified 4-arm trial, but it is not randomized, so it is going to be based on your molecular phenotype of your tumor. These are the 4 treatment arms. Again, the goal today is not for us to debate whether or not these are the 4 right therapeutic components. I think everyone's probably comfortable with the XRT. You could ask whether there's really good data for bevacizumab, and we won't really discuss that. This is being given concurrently with the radiation therapy. For patients whose MGMT promoter is not methylated, remembering that the way this works, if it's not methylated, then you're producing the resistance enzyme that makes you unlikely to respond to temozolomide. So if you're not methylated, you don't get temozolomide. If you are methylated, then you're not producing the resistance enzyme. You do end up getting temozolomide in those 2 groups. Similarly, if you're EGFR negative, you don't get erlotinib. And if you are EGFR positive, you do get erlotinib. You can clearly put together, therefore, a kind of control group that is negative for both of the options, and then the 3 groups that are either drug alone or in combination. So I have to admit, I wasn't expecting Darren to say what he said, and I thought, certainly in the United States, every time we try to raise the issue of biopsy, it ends up as being a big argument of, oh my God, it's been shown unsafe and you shouldn't be doing that. And so he kind of laid it out where he almost, I think, set the audience up to say, it's clearly time we should be biopsying. So this may not, I may be preaching more somewhat to the converted, and if so, that's good because it just makes it a little easier. The arguments in the United States are, oh my God, it's a horrific procedure and will kill everybody and you shouldn't be doing it. And yeah, I guess if we were talking about some of the old technologies, that would basically be true, but clearly that's not the way we operate anymore. This, for example, is one of our intraoperative facilities. You can see the surgeon's fingers actually inside the brain while they're operating. So this is not a question of not knowing where you are or what you're doing. These are kind of becoming much more standardized techniques. But it's not just in terms of knowing where you are, it's knowing what's around. This is a patient inside the intraoperative MRI suite. You can see that the reason the skull is open here. So this patient's brain is actually open and exposed on the table. This is a imaging sequence. The green is the tumor here. This is actually an adult patient, but we do them in pediatrics as well. You can see all the vascular structures. You can see the cerebral spinal fluid flow tracts. You can see all of the white matter tracts, including some that are passing right through the tumor, that are going to raise issues about the kind of surgical resection that one would go after. Obviously, particularly in certain areas, this will be less so in the brainstem, is you also want to know what some of the functional areas are. So these are functional MR. This is an adult that's awake, that's actually responding to commands so that they can actually map some of the functional areas, some of which are in this light blue aqua color here, to ensure that you're only going to take an operative route that avoids some of the critical structures. So again, it's no longer a question of back in the 60s and 70s where surgeons were blindly going in to try and find stuff. The other thing that we discovered is when surgeons were often presented with the opportunity of doing this, I think many of the reasons that some of the biopsies were either non-diagnostic, particularly earlier on, or low grade, is what they were doing was they were going to the very edge, probably around some of the reactive tissue and biopsying that, which meant that they could go to everyone and say, I biopsied a brainstem tumor, but what they were really doing was going, barely touching the orange peel, let alone getting all the way deep inside, which is obviously where the informative tissue is going to be. So based on what we think are many of the new developments, and these are the ways that we're currently doing our procedures, we feel actually very confident in our ability to get the kinds of tissues that would be required. And as I've said, in consultation with the other sites, I think this can now be done on a multi-institutional level. I should point out that Mike Prados and I first proposed this idea 10 years ago and got yelled off the stage year after year after year. And then Mike Prados, who is the head of one of the large adult consortium in the United States, came up with a very good idea, which is instead of maybe 2 oncologists getting up and proposing biopsy, why don't we get a neurosurgeon to stand up and give the same proposal? And so Nalan Gupta got up and gave the same proposal, and it has gone forward ever since. So as you are thinking about strategies to make things work, there are some opportunities there. You've already heard a little bit about this data. This was the French study of 24 patients, 2 of whom had some transient cranial nerve deficits, but all recovered, no mortality. Similarly, there were 2 patients in the United States that underwent convection-enhanced delivery. I think somebody else is going to talk a little bit about convection-enhanced delivery later on today. But just to remind you, this is where you insert catheters, in these 2 children were inserted into brainstem gliomas, and then under high pressure, fluid was infused into the brainstem to basically surround all of that. So whether you're taking a little bit of tissue out or you're putting stuff in, it turns out that at least in relatively small but well thought out studies, this is a safe procedure, and obviously safety has to be paramount. The treatment plan, without going through the details, standard radiation for all the equivalent of what the COG protocols would be, because we wanted to keep the criteria as close. We're just going to use the standard dose of bevacizumab, the standard with radiation dose of 90 milligrams per meter squared. So these are identical to the way it was done in the large COG study, the curve of which I showed you at the very beginning, and then followed by the every 5-day maintenance in 28-day cycles, and then Tarceva at 85 milligrams per meter squared per day. As most of you are aware, actually, and in fact, as you saw from the data already presented, this might actually even be a little bit of an underestimation of the dose, but because it's going to be potentially combined with other things was why we chose that dose. And again, if we waited until the entire world was comfortable with all of the dosing and timing, for sure the protocol would never go forward. So I'm going to leave this part now because although this is clearly how we think we are going to move to the next step, and I think it's a reasonable first step in that it does offer patients an opportunity to guide therapy based on their child's tumor, not some average of what some of the pathways are in individual tumors. I think this is justifiable both from an ethical point of view as well as a scientific and perhaps most importantly from a clinical point of view. Do I think that by stratifying the groups into 4 that we are suddenly going to have a cohort of long-term survivors? I don't think so, but even if we can just begin to clearly show that there is a group of patients doing better longer, you sometimes have to crawl before you do anything and then learn to walk before you can run. And to some extent, we are committed here more to the long-term success of this. We're not just going to keep throwing darts blindly at the board, hoping we hit a bullseye with no attempt to actually kind of guide it there in the first place. So what I'm going to do now is switch to the other side. And again, unfortunately, I've taken out all of the data-specific stuff that's still embargoed and therefore can't talk specifically about it. So I apologize that I'm going to keep referring to stuff that I'm not actually showing you. But I think the concepts here are all valid. And that was when we first approached this concept of how we were going to move forward, we recognized that there were a couple of things we needed to do. That doing the immunohistochemistry of EGFR or PDGFR, you could choose your 5 most favored molecules, do the immunohistochemistry, and see whether the tumor has those or not. but that cancer is far too complex in order for that to be a long-term successful strategy. And to some extent, we feel like we've almost exhausted the immunohistochemistry options anyways. So we decided if we were going to do this, what we were going to need to do on every single sample was be able to gene chip the entire genome. We were going to have to sequence the entire kinome, every receptor tyrosine and kinase, since that's where many of the signal transduction pathways originate. We were going to need a full epigenetic analysis of every chromosome, since particularly in pediatric tumors, remember, we saw some of this today, these are tumors that don't typically occur in adults, and in fact, they even occur younger than most high-grade tumors in kids, suggesting that this may be an epigenetic phenomenon of a process that in development was active and then was meant to stop after you were born, but that because the signals in the pons never got that off signal, is why we see this kind of unique distribution of these tumors. Do I know that to be true? No, but if we don't set up the methodology in which to begin to answer those questions, it's going to be very hard to figure it out. And as I'm sure Alberto is going to show you with some fascinating data from autopsies, we decided that although autopsy data is going to be critical in terms of helping us understand, it's a little bit like looking at trying to understand what made a prisoner, a criminal who has since died, trying to go back into their life and understand what made them go bad in the first place. And obviously, it's much easier to look at them in childhood and begin the analysis then than wait until after they're gone and then try to go back and recapitulate the story. So I'm just going to show snippets of data. This, for example, these are pediatric low-grade astrocytomas. And so these are about 200, and in this case, 261, in which we gene chipped the entire genome. And there are a couple of things that you'll find here. And again, the discussion of this data is not critical, other than you'll notice that, for example, pediatric low-grade gliomas, which tend to cluster together, suggesting that these are unsupervised analyses, so the data that's coming out is by virtue of the pattern recognition of similar groups, is that you can see that most pediatric low-grade gliomas share a lot of homology amongst themselves, although they do break into some groupings. So these groupings have a lot of similarity that's different from these, but those pediatric low-grade gliomas tend to still fall together. By contrast, if you take an identical grade 1 or grade 2 pilocytic or grade 2 fibrillary astrocytoma from an adult, which a neuropathologist would tell you under the microscope just looks like a grade 2. They couldn't tell you the age of the patient it came out of. In fact, you'll see that the adult low grades all separate into a completely unique gene classification category, suggesting that although we can't see the difference, the differences are there. I'm not going to go through any of this data other than to say that all of this is now being done only on paraffin, so we no longer need fresh frozen material. And so one of the things we did here is we just took archival tissue, because in this way, not only do we have the tissue, we now know which children are going to have relapsed, which ones are going to have died, which ones ended up having NF1, even if they were too young to make the diagnosis at the time we did it. And we can now therefore go through and kind of analyze both retrospectively and prospectively, if that makes any sense at the same time, to begin to put some of these patterns. I'm not going to go through this in more detail, other than this will be a fundamental part of the analyses that we're going to do for the Pontine gliomas. So obviously, we didn't start doing this in pediatrics. We began doing this by taking a large series of adult tumors, including some brain, doing a standard genomics profile, and then identifying a number of mutational abnormalities, which led us to this concept, particularly for many of the tyrosine kinases, in which over and over again in cancer, there appear to be a few kind of smoking guns, I guess one would say. And so what we did in kind of recognition with the adults as we were working on the platform was to say, okay, if you have a c-KIT mutation, clearly your patient wants to be on Gleevec. The issue, of course, is that as you begin to think about cancer, not in terms of, notice I didn't say that this patient actually had had GIST. I just said that they have a c-KIT mutation. This is the drug that they should be on. And in fact, to some extent, although we spend a lot of time convincing people they ought to want to become neuro-oncologists, to some extent it's becoming a little less important what you call yourself, because as we move forward, the oncologist for this child doesn't need to be a neuro-oncologist or a breast oncologist. What they need to be is an understanding of both the KIT pathway, the HER2 pathway, and in this example, the VEGF pathway, because if that's your child's tumor, then you need a combination of drugs that match that. And it doesn't matter whether this started out as a breast, a colon, a prostate, or a diffuse intrinsic Pontine glioma. And this conceptualization of this being the way to move forward, which I believe strongly, as a biologist, obviously, I think biology cures all. We just have to figure out the answers, means that what we're going to do is apply that philosophy to diffuse intrinsic Pontine gliomas. Now, when we were looking at some of this, we went back and we kind of validated some of this. So if you take, this is all done from adult cancer, so this is not pediatric data. If you look at breast, colon, the usual players in adults, for example, RAS mutations, there are a lot of RAS mutations in adult cancers. Almost all of the mutations fall into a relatively small number of codons. So if you want to know where a mutation in RAS is, you just have to look at those three and you've basically answered your question in all but basically 1 in 100 patients. Now, in pediatrics, since we're used to dealing with everything that's rare, we always worry that in pediatrics, which may be different from adult tumors, this may be the one, so we were a little worried about that. And obviously, as you go to other tyrosine kinases, you begin to notice that some of the incidence falls off. So where are the other 5%? Where are the other 20%? And as you go down into other ones and those numbers continue to fall, you recognize that although we know a lot of the mutations, we don't know them all. And so we said, well, then let's go backwards and redo some of that analysis. And this is part of the methodology that I'm not going to go into other than, so I apologize for the stuff I've taken out, but you just have to believe me that it's sensitive, accurate, high throughput. It's cost effective if you've got a lot of money, and it's relatively flexible in terms of the terminology. And it has now been linked with this mass array 7K, looking at mass spec, and I'll explain why some of this is important in a moment. Let's not even bother with this. These are just validation steps, so let's not worry about those. What we did is we used the platforms, and if you're wondering, can you just buy one of these platforms, the answer is no, unfortunately not yet, although that will be coming. And I don't own any of the rights or technology, so I can say this freely without feeling like I'm trying to earn myself more money. The Harvard Institute at Dana-Farber decided many years back to create a new institute called the Broad Institute. And the Broad Institute is made up of half of the people in the Broad Institute are people at MIT, which is a technical institute in Massachusetts, and I think really one of the leaders in the world for nanotechnology and bioengineering. And so the institute is basically made up of half oncologists and half bioengineers, on the assumption that if you put those two together, they would either have no idea what each other was doing, or they would start to come up with all kinds of really fascinating ways of analyzing biology in a much more engineering format. And that's basically how a lot of this got settled. And so they're in the midst of patenting and doing all of the stuff that they do to do this. Our opportunity is to actually get the answers, which is obviously what drives us on our side. So what they did is this is the adult, so I was not part of any of these studies, is they basically went back into a whole bunch of adult tumors. They took 1,000 tumor samples from 17 major groupings, prostate, breast, colon, et cetera, and began asking questions as they analyzed these. And a standard assay for some of these would be somewhere in the range of about 150,000 PCR reactions per testing. So this is not the kind of thing you would drop on your postdoc on a Friday afternoon type thing. There is a whole robotic system that was developed in order to be able to do, as well as an entire computational system in order to actually read that volume of data in order to tell you what to look at. But if you actually look at some of these, what was discovered was that we could find nucleotide substitutions within the activating domains of a variety of receptor tyrosine kinases, and that in fact the reason this is particularly important, and one of the reasons we decided to focus for for the current project on this is there are already small molecule inhibitors of every one of the ones in a red box here. So the idea wasn't just the pure biology of finding a mutation, it was finding a mutation we might actually do something about. Obviously, this list is going to continue to expand, and as it does, it simply means our treatment opportunities will expand as well. This is another example. These are the genes here. These are some of the tumor types. You'll notice that there are some, like this is polycythemia vera, which basically is a single, almost all cases are from a single mutation. Other tumor types have all kinds of different mutations in different places, and this is important because you're going to have to figure these out, particularly as the cancers become more complex. As I said, we started with pediatric low-grade gliomas, which are probably the least mutational and simplest of all of the tumors. It was not by accident that we chose the simplest to get started, and clearly the diffuse intrinsic pontine gliomas are going to be more complicated, but fortunately we have started to figure that out. One of the most important things is when we went back and looked at some of those tumors, sarcomas, breast, colon, prostate, but this time not saying, okay, you're a sarcoma, so you should have, these are the kinds of mutations you should have. What we did is we sequenced every single kinase, all 500 in these tumor samples, and discovered, for example, that there are many sarcomas that have the BRAF V600E mutation. Now, as many of you know, there is a drug, the RAF265 agent that actually targets this pathway. And unfortunately, of course, for a sarcoma patient, you would never even analyze this because 99% of sarcoma patients would never have this mutation. And if you tried to run a clinical trial, you'd have a response rate of 1%, which of course would be a failed trial. But again, if instead what you did is you do this and then say to the 2 sarcoma patients here, it doesn't matter that your tumor is not a melanoma, you need to be on this drug as part of your therapy. Now you really begin to personalize the medicine based on your mutational status, not on what somebody under a microscope says is the classification of your tumor and therefore the type of therapy. And if you go through these, all of the findings here are not mutations that would have been expected for these tumor types, and yet in every one of them, it was a mutational activation within a receptor tyrosine kinase that was identified. Now, the skeptics in the room would say a mutation in an activating mutation in a receptor tyrosine kinase does not equal pathogenesis, and therefore you can't prove that inhibiting some of these will actually change the course of those disease. But what better place to start than in mutations that are major causes of most of the known cancers in the world that are now being found in tumor types other than those classically analyzed. The other thing that was going to be important for the technology, because once we got away from low-grade astrocytomas, we anticipated that many tumors would probably have multiple mutations in multiple pathways. And although that's probably more going to be an adult phenomena than a pediatric phenomena, this is a technology, because it sequences each receptor tyrosine kinase separately, means that you can find tumors that have multiple mutations in multiple things and allow you to start putting together these cohorts of treatments so that one patient needs to be on Gleevec, Iressa, and Temodar, whereas another patient needs to be on Avastin, whatever and whatever. And fortunately, the technology allows us to do that. So as we kind of talk about where this OncoMap takes us, one of the questions was how to expand the mutational panel so that we could find every single mutation in every part of the coding sequence, increase the multiplicity of the assays so that you could do this faster, better, and in particular with respect to diffuse intrinsic pontine gliomas with less material, because obviously if you're going to provide a simple 4-pass pathology as the bulk of the material on which you can do all of the studies we want to do, everything has to be scaled to a nanotechnology. That everything needs to be done in paraffin embedded material instead of fresh frozen. And everything I have showed you so far, none of those analyses were done on fresh frozen material. Everything here is paraffin, and much of that data, what we did is we just went back 10 and 15 years and pulled blocks that have been sitting there collecting dust for many years and are able to do these analyses, which means the pathologist can take all of the material they need, they can fix it to be sure that they've done whatever diagnostic criteria they need, and then we can take the paraffin material after that and do what we want without having to worry that we've used up their fresh frozen and then there wasn't enough to do the pathologic analysis. the whole system has been automated, not just with respect to the assays, but also to the calling of the mutations. We won't go through that, although for those of you that are involved in some of this technology, for every one machine that does an analysis, there can be 50 people poring over that data to try and understand it. So this automation actually turns out to be critically important in terms of actually coming to some conclusions. And these are just, again, more unique mutations that were identified that were otherwise unanticipated when we went through this panel. So the last thing I'm going to show you is just, here's a bit of a proof of principle, and although I've taken out all of the original data slides, so what we did was we took those 260 original genomed low-grade samples. These are all from paraffin-embedded archival material, and we basically now sequenced their entire kinome. Kinome has kind of become the euphemism for the entire sequencing of all activating kinases. And this is an example of just the analysis for one molecule. This is BRAF. So this is BRAF analysis in 156 paraffin-embedded pediatric low-grade astrocytomas. And you just have to believe me because I could have put the dots anywhere. If you're on this line, it means you're normal. If you're on this line, it means that you've got a mutation, and in fact, you can separate out the types of mutations just based where you sit on these curves. That's not critical, I think, for today's discussion. No. And basically what we discovered is out of those 156 samples, about 25 of them, i.e. about 15%, have one of the V600E mutations. I'll leave it at that. Obviously, we, in some of our genome work, though, had noted that there were abnormal signals associated with the BRAF gene that did not get picked up on this mutational analysis. And when we went and looked at those patients, what we discovered is they don't have a mutation of the gene, they have amplified the gene, because obviously there's a couple of ways to activate BRAF. One is to mutate it, the other is to simply give the cell a lot more of it so that it continues to signal on a much more frequent basis, and it's exactly what we picked up. In fact, we've now identified these signaling pathways in about 50% of all of the low-grade astrocytomas, and we can actually separate out them by both grade and location, data that I'm not going to go into today, but here's an example of how all of this technology can be equally applied to the diffuse intrinsic Pontine gliomas. This is the last slide, and again, I'm not going to show any of the specific data for it, but when we recognized that as the sample sets got smaller and smaller, the ability to go down to single cell and single molecule sequencing were going to be critical. And to some extent, they were in recognition of, again, some of the points that you already heard about, and I swear we didn't talk beforehand. We recognize that the heterogeneity within diffuse intrinsic Pontine gliomas means that you can't just take a big sample, put it in a blender, and then get the average signal. Remember, that signal is made up of the normal neurons, the normal astrocytes, the normal connective tissue, the tumor cells, the reactive cells, et cetera, et cetera. And to try and figure out a signal when you're looking at the average of all of those signals really becomes somewhat unfunctional. And therefore, what you really needed to do, you probably want to take some of the normal matrix cells and analyze them. You're going to want to, with laser capture dissection, take out some of the tumor cells and analyze them. You're going to want to look at some of the stromal cells and analyze them. And those are the pictures you are going to have to come up with if we are going to really understand. I hope most people in the room agree that cancer is not a disease of a cell out of control. A partnership of that cell out of control has to be the environment in which it lives. Otherwise, it could not do what it does, which means if you don't understand the home of the tumor cell, it's unlikely you can really understand what drives that tumor cell. And therefore, the ability, we've now got a chip that runs in these single molecule sequencings. We can basically do 2 gigabytes of analysis per run. At about 250 megabases per lane as these chips are running through in this free run system. So that again, as you begin to ask in very small areas in regional compartments, how do different parts of the tumor behave. Obviously, you could also do this both pre and post progression, diagnosis, and at relapse. So one can envision for a variety of both tumor types and analyses, this offers a huge potential to begin to get at the very basic of both what went wrong and what kept going wrong. And just before I started speaking, I'd spoken to Alberto about how we would love to do some of this on his paraffin samples, where we could actually begin to go back. Obviously, that's after the fact, but as we begin to compare to some of the initial analyses of the upfront patients, this provides an opportunity to do some of that comparison. And I think, so this is a summary, but since I already told you most of this, we'll end there. Thank you.